All right, let's continue on with what are we talking about? NMR. Let's see how far we got yesterday, or whatever day that was. Okay, we talked about different types of hydrogens, chemical shifts. Okay. Okay, cool. So I have just a couple more bits about chemical shift to share. The last little bits here. So with chemical shift, we're focused, the more obvious chemical shifts are for alpha hydrogens. So we saw that, for example, these ones, which is CH3, which is 1.0 plus, what is it, carbonyl 2.0. We would expect these to be around 3. We would expect this one to be, 1.2. Kind of terrible remembering the numbers, but I think that's what we have, in the 1.7 for methane hydrogens. Um, these guys way over here a beta position, so 2 carbons away, they do feel it just a little bit, and it's usually about a fifth of the. Now that I'm thinking about it, was it 2.5 for a ketone? Let's check this real quick. Oxygen, carbonyl. Oh, it's +1. Oh, I'm just lying to you. That's what's going on. Okay. Sorry about that. Usually, when you're looking at a beta hydrogen, the effect is usually of the alpha. So usually 20% of it. So 1/5 of the effect. So we're going to see that these ones will probably be about we're looking for about 1.2 there. So they will be shifted ever so slightly just due to inductive effects. And as a result, you'll have slightly more downfield than you'd expect them to be. Not really something I'm terribly concerned about. Not a huge problem. And so anything that's beta to one of these things that we talked about, the halogens or the carbonyls or oxygens or whatever, that's about 50%. I'm sorry, about 20%, about 1/5 of those effects would be for things beta to them. So, same thing here. We've got a chlorine. This would be the alpha position. This would be beta. So for a chlorine, right, we saw that a chlorine is going to put it up by about 2.1, thereabouts. So this one we're going to see 1.2 plus 2.1 is 3.3. This one we would see it's 1.2 plus, let's say, about 0.4-ish. Or we see it about 1.7. And then this one we'll just see plainly at regular old 1.0. Gamma, there's no effect from the chlorine. It's too far away. So things have to still be kind of close for them to start messing with your chemical shift. So there we have that. So that's the last thing I wanted to say about chemical shift. So yeah, we're good. Well, not really. Do I want to talk about anisotropy? Talk about benzene for a second. We know that deshielding the nucleus moves it, shifts it downfield, right? And we know that deshielding means that we are kind of removing electron density, right? Whether that's by putting an electronegative atom next to it or a carbonyl, which has inductive effects that's going to withdraw electron density away. Something about removing electron density, right? We know, though, that the benzene, those electrons are completely delocalized. We often draw it as the ring, right? These electrons, they're completely delocalized. And as a result, because at any given time we may not have any electron density at a particular site, this is called anisotropy, that we have these pi effects happening right next to, when we have these pi bonds moving around like this, we have this phenomenon of anisotropy. And because of that, we now have this whole thing that's creating its own magnetic field as these things are going on. So all of these, they're completely delocalized, and they kind of make their own magnetic field. Because these electrons are constantly zipping field. They're zipping around. So if we think about them, they're constantly moving around. They're creating their own magnetic field, and that's going to completely um, disrupt the normal interactions we would expect to see. And so this magnetic field is much stronger than a plain old regular proton moving around. And suffice it to say that we end up shifting this far down field. And that's why aromatics, they show up around 7 ppm, is because of this anisotropy. So these electrons are making their own magnetic field that's going to interact in different ways, and we're going to end up completely deshielding these nuclei. And so as a result, we see aromatics around 7 ppm. I don't need you to know about the theory of anisotropy or how this all works, just accept it. Aromatics show up at 7 or so. And this reason is also going to be why they're not going to split very nicely. The shape of aromatic protons is also very weird, as we're going to see for aromatics. So aromatics, the peaks are not normal like we're going to see with some of these other ones. We're going to predict their shapes because their shapes will tell us a lot of valuable information. For aromatics, they're less reliable, shall we say. All right, the shape of the peaks. However, they're going to show up around 7. All right, so that's it for chemical shift. Let's see, what did I do third? Was it shape or integration? Let's quickly double check. Third, I did shape. Okay. All right, let's talk about peak shape. Suffice it to say that hydrogens are affected by nearby non-equivalent hydrogens. And it just depends if they are spinning the same way as each other. And we're going to see that because of this, because half the time they'll be spinning the same way, half the time they'll be spinning the opposite way, that their magnetic fields will interfere with each other a little bit. And as a result, we will end up splitting our peaks. And so, if we look at, here, let's make this a little bit more interesting, at these, if we're just comparing these two, if we're comparing the green one with the purple one, I mean blue, let's see how the blue affects the green ones. The green ones are all equivalent, right? They're all on the same carbon. They're just rotating around. They're all equivalent to each other. These green hydrogens can be affected the blue hydrogen. And we're going to see the opposite is true as well. The blue hydrogen will be affected by the green ones. But if we look at this, suffice it to say that blue one, if we're looking at any of these in particular, whichever one we're looking at, we'll say that one's HD. Well, let's not even do this way. It can have the same spin as HD or the opposite. So HA or HB or HC can have the same or opposite spin as HD, the blue one. And as a result, we're going to see that some of the times we're going to have higher energy peaks and sometimes lower energy peaks. And so we would normally see, aha, here's our normal signal. Our normal signal will then get split into two peaks. It splits your peak because one peak tells you one energy, right? But we're going to see that we're going to have different amounts of energy absorption depending on how those two interact. If they have the same spin, they can help each other out. If they have opposite spin, they can hurt each other, right? And so we're going to end up splitting our peak in two because we have a hydrogen here, HD, that can split hydrogens A, B, and C. Hydrogen D, on the other hand, HD has 6 neighbors. Those three had just one neighbor, so it splits in two peaks. We're going to see that HD can also be affected by every single one of those green hydrogens. And so it just depends on how it's going to look. We're going to see that it's pretty easy for splitting a single peak in two, but for splitting a single peak in two, the first hydrogen, let's say, oh my gosh, I'm going to now change all these. Yeah, whatever. I'll keep this as D. That's fine. If we see how HA interacts, well, that can split that into two peaks. One of higher energy, one of lower energy. And then we can say, well, how does HB interact with it? Well, HB does exactly the same thing. It'll keep splitting it. But now look, two of those have in fact lined up with each other. So we'll need to keep that in mind later. And HC will now interact with it. And these are all equivalent, HA, HB, HC, right? So they're all splitting equally, and etc. We're going to see that this peak will look like this. We will end up with a septet, is what this is called. We have 7 peaks, which comes from 6 neighbors. And so we're going to see that splitting occurs by the n+1 rule. So if you have one neighbor, you're split into 2 peaks. If you have 3 neighbors, you're split into 4 peaks. And we're going to see that these follow Pascal's triangle. So we see here that we kind of have this predominant peak in the middle of our septet. We have smaller and smaller peaks as we go to the outside. If it's split into 2, those 2 peaks are equal to each other, because that's just this kind of first division here. Half of them go higher energy because they are the opposite spin. Half of them go lower energy because there's the same spin. We have synergistic effects there. So we take half of our protons, move them up, half move down. That's a doublet. They're equal. A triplet, on the other hand, looks like this. We're splitting it twice. And if we see the second split, say this one had a value of 100, that means 50 of them went that way, 50 of them went that way. If we look here now, 25 are going to go that way. We're going to just keep splitting this in half, right? And so a triplet will actually have 25, 50, 25. These two will get added together because they're split and they cancel each other out. So we're back to 50 in the middle. So we see a triplet has a 1 to 2 to 1 ratio. And if we split this some more, actually, no, these are 25s here. We see a, suffice it to say, I'm just going to show you. A quartet has a 1 to 3 to 3 to 1 ratio of the intensity of those. And this is Pascal's triangle that we see here. Let's hop over to Wikipedia. Oh, my mouse is off. A sec. There we go. Let's do a new tab. Pascal's triangle. Okay, and let's swap this screen over. All right, so Pascal's triangle will tell us the ratios. So for a single peak, right at the top here, we have a 1 in it. For the second for a doublet where we split it once, they're still of equal proportion to each other. For these are all the ratios. If we have a triplet, it's a 1 to 2 to 1 ratio. If we have a quartet, 1 3 3 1, a quintet, 1 4 6 4 1, etc. What's important to note is every other one you have symmetry, or there's always symmetry in there. But with the odd ones, you'll have a strong peak in the middle, and the other ones you'll have two strong peaks in the middle, like 3 3 10 10, and so on. So Pascal's triangle works for us for splitting trees. Because all those hydrogens were equal to each other, right? All those 6 hydrogens that split that poor isopropyl hydrogen 6 times, we end up with 1 to 6 to 15 to 20 to 15 to 6 to 1. You don't need to memorize these numbers by all means, by any means, but that's why it looks like this. So we have that one in the middle, that's the 25. Then we got 15s and 6s and 1s out there. It looks like a little mountain. But that's the idea. A quintet has one big one. Looks like that. That means you have 4 neighbors. And then 6. And then the 5. This is a sextet and a septet. These tell you how many neighbors you have. And so, just looking at the shape of your signal, we see an isopropyl group like this will give you a septet and a doublet. Your blue H will be the septet, sorry, and your doublet will be all these, etc. All those green hydrogens will be the doublet. An ethyl group, on the other hand, if we look at an ethyl group, we've got 2 hydrogens next to 3 hydrogens. We're going to see that, what color are these ones? This one will be a quartet because it's next to 3 hydrogens. Do we see that on the neighboring carbon we have 3 hydrogens? So this will be a quartet. The orange one will be a triplet because it's next to 2 hydrogens. So an ethyl group is always a triplet and a quartet. This one is a little bit less common to see, but the isopropyl one is very obvious. If you have a septet and a doublet, usually that's indicative of an isopropyl group somewhere in your molecule. But we can see here that this is giving us more information. Now we know not only the chemical shifts of these things, but we also will know, well, now I have information about the neighboring hydrogens. So this information will tell us, okay, what's nearby this? So chemical shift tells you like heteroatoms nearby it. The splitting tells you about neighboring hydrogens. So do you have an isopropyl group? Do you just have a methyl group? Whatever it may be. No neighbors, by the way. You have a singlet. We would just see a singlet for this molecule. These are all equivalent hydrogens. They don't split each other. And so as a result, we have a singlet. And we can even say this one is going to be about 2 ppm. That's all we're going to see. One singlet at 2 ppm, and it would have an, I can't say it's an integration of 6 because we haven't learned that yet. But we'll see. So for this, all we're going to see is a singlet at 2 ppm. So if there's, so a couple things here. No neighbors are going to be a singlet. Equivalent hydrogens do not split each other. So all of those hydrogens on the methyl groups, they do not split each other. So HA does not split HB, which does not split HC. They don't split each other. They're equivalent to each other. And so we're only looking at splitting one carbon away. We're not going to worry about long-range coupling in this class. And last thing to note is that H's on heteroatoms do not split. So we have 3 types of hydrogens here. Let's see where we're going to find them all. We're going to see, excuse me, I'm going to just label them now specifically. So HB, HB, HC. HA, we're going to see that this has 6 neighbors because we're not going to count hydrogens on heteroatoms, only things 1 carbon away. So we're looking at neighboring carbons and the hydrogens on those. So this one will see 6 neighbors, so it's going to be a septet. And we're going to see that one probably because it's an alpha hydrogen to an alcohol. What is that, about 1.7 plus 3? We'll see that about 4.7. Or is it 2.5? No, it's 2.5, isn't it? So 4.2. I think. I'm terrible at remembering these things. I want to give these to you so you can use them, but I need to remember them. It's 2.5. Okay, so we'll see a septet at 4.2 ppm for this. For HB, we're going to see a doublet because remember the hydrogen or the we're looking at hydrogens 1 carbon away. So all those blue hydrogens see HA, and that's it. They don't see HC. And we're expecting those, since they're beta to the oxygen, we're going to see that those maybe are going to be about 1.0 plus 0.5, maybe about 1.5 ppm or so, thereabouts. We're predicting this. That's a methine there, Kevin. HA is a methine. CH. Only 1 carbon on that. No methylene carbons in this molecule. If we were to write this out, CH3, CH, CH3, OH. So CH, this is a methine. Hopefully that addresses that. Yes. HC, of course, the mystery one. Hydrogens on heteroatoms are weird. They will always be a singlet, but broad. And this will be somewhere between 2 and 6 ppm, somewhere in there. I see what you're saying, but no, we're looking at the numbers of hydrogens on these. So think of it that way. A little bit easier that way. So, yes. So with these, this is what we're expecting to see. Again, reality, it may be slightly different. That's okay. I mean, this broad peak for HC is going to be all over the map. We don't know. Let's take a look. Let's see if we can't Google this spectrum for isopropanol and see what we get. Isopropyl Nmr. All right, let's take a look. So with this is the NMR of apparently isopropyl alcohol. Hey, they got a pretty good peak for their alcohol. Good for them. What are we looking at here? So, zoom in. Notice what we do see. We're looking at a peak about 1.2, thereabouts. It is a doublet. As we can see, we have 2 peaks here of relatively equal intensity. We expected a doublet at 1.5. In reality, it's about 1.2, 1.3, somewhere around there. Pretty close. We have here at 4 a septet. Notice 1, 2, 3, 4, 5, 6, 7. Interesting, we are having some splitting from the oxygen hydrogen here. That's, well, we don't worry about that. And then here we have our singlet. In this case, our alcohol one is showing up right around 2.2 or so. So we see that these rough guidelines they're kind of useful, but they are rough guidelines. So, oh, y'all can't see the thing. So there's the scale for our ppm. So that's what we're looking at here. All right, so our predictions are working out. That's a good thing. We're looking at that. So that's what we're seeing with these things. So I'm not terribly focused on the exact numbers. Don't worry about that too much. These are just predictions. This is a way for us to take a molecule and figure out its NMR spectrum. The harder part is going from the NMR spectrum to the molecule. But we're going to see how to put all these bits together. All right. When double bonds are involved, though, we're going to see that the splitting gets weird. So we're not going to have as normal of splitting patterns as we would like to see when we have, let me get the table of J values here. Right. So with double bond, splitting gets weird because they see things differently. So we're going to see that there are a bunch of coupling constants for hydrogens. Is there a table in here, roughly, of the coupling constants? I don't see one very nicely. But suffice it to say, the coupling constant for hydrogens, we're going to have different types. This is chapter 15. See what I remember. For trans, I think we're looking at 17 hertz. For cis, we're looking about 12. For geminal, we're looking at 7. And for vicinal, we're looking at about 2 hertz. I think this is, if I remember correctly. I don't remember the exact values. It's not important. But we're going to see here that all we've done so far is use this one. This gives us our n+1 rule. We split each peak by 2 hertz. That's not terribly important. I don't really need you to memorize this number at all. But they are pretty straightforward. They all just subtract by 5, right, to get each one. When we're looking at other things, though, this would be a trans relationship. When we're looking at hydrogens on double bonded carbons that are trans to each other, those will split each other quite a bit more. We're going to see that for this molecule, HA and HB are going to look very different. So cis and trans we know. Geminal means they're on the same carbon. So in fact, I could make... let's look at the geminal one later. We'll look at this one later. This would be a geminal relationship. Cis and trans, we know. Geminal means they're on the same carbon, and vicinal just means they're the normal ones we're looking at one neighboring carbon away. That's for plain old n+1, that's things that are one carbon away. What's weird about this is because they have different coupling constants, all the vicinal ones had about 2 hertz of a difference. So ones that will shift you up by 2 hertz or down by 2 hertz. It's very small in terms of like the actual like ppms, but those will shift your carbons away, right? And so when we looked at that kind of septet thing that I kind of just abandoned, these were all splitting by 2 hertz. And so we did see, well, it's 2 hertz. Those are all vicinal hydrogens to each other. So they all split by 2 hertz. They all split equally, which is why we get these lovely, nice patterns here. The n+1 rule comes from the vicinal splitting. But when things have different coupling constants, they split weirdly, complexly, we'll say, in a complex manner. So if we are looking at some of these H's, if we're looking at HA, let's see how HA is going to be split. We're going to see, well, HA, it's going to see everything that's one carbon away, and it's going to see them differently. So it's going to say, well, we have HC that's one carbon away, and that's vicinal. It's plain old sp3 carbon way over there, HC. It's got its isopropyl group, it's going to be over there. Coupling constant for HC to HA, we might describe it as JAC, is 2 hertz. HA also sees HB, and that is a trans relationship. which is 17 hertz. So we might say JAB is 17 hertz. And how we're going to split these is we're going to do the higher one first. Here is HA we're looking for. We're going to split this thing quite a large amount this time because we're doing the 17 hertz. The big one. So that's going to split our peak into a doublet. We have one that's HB. So HB will split our HA peaks quite a ways apart because it's a large coupling constant. And now HA also sees HC, and so we're going to now split by 2 hertz each of these. And so instead of seeing a triplet, we're going to see what's called a doublet of doublets. So first HB splits it, and that's the far away splitting. Then HC comes in and splits that further. And as a result, we have now a doublet of doublets. We have a doublet, so those two are pretty wide apart, and then all of those split in two as well. So previously they lined up, right? We saw, aha, we make this, and then they lined up again because everything was 2. When everything was 2 hertz, things lined up. And so we end up with our triplet with the 1 to 2 to 1 ratio, right? This was a normal triplet. Because they have the same coupling constants, they just make a nice triplet for us. However, because these have different coupling constants now, they see each other differently, we form a doublet of doublets for HA. So it sees HC and HB, those are the hydrogens on adjacent carbons, but it sees HC differently than it sees HB. HB it's much more affected by. And that's just some of this that we're going to need to learn. And so we get a doublet of doublets here. All right, so let's take a look at the next one. Let's look at HB. Let's see, how is HB going to be split? How is HB going to be split? What does HB see? Well, HB sees HA. That's a trans relationship. 17 hertz. HB sees HD, but there are 3 of them. Sorry, this is HD. Sees 3 of them. All of them at 2 hertz. So we're going to have to split 4 times total. First one by 17, the next 3 by 2 each. So if we take HB and split it, sorry, I'll be consistent, I think. Big split first. This is our 17 hertz. We're going to see that now we're going to split it by 2 hertz. This is our first HD. And now our second HD comes along. And because these are equal, we're going to get those to add up. And now we have our third HD, which is going to split these even more. And so we'll end up with an I. We have now a doublet of quartets. Isn't that absurd? So we're going to see for HB a doublet of quartets. So we're going to see two quartets there as a result. Because of this weird splitting. So HA shows us a doublet of doublets. HB shows us a doublet of quartets. And y'all thought we were done. No. Actually, we are. Because HD is going to just be plain old doublet. HC will be a 7 plus 1 is 8. It'll be an octet, I guess. So HC will be different. But these are the weird parts. Those will be normally split. So everything that's on an alkene can split weirdly. All right, and you always will do the higher one first. So if you have a God, let's do this geminal thing. All right, geminal thing. Let's look at that one. Yikes! And in fact, let's make this one HC, just to make things more complicated. So if we look at HA, it's got AB, we have AC, and that's it. We have 7 hertz for this one, and I'm sorry, that's the wrong ones. This is 7 hertz. These are the geminal relationship. This one is 17 hertz. HB will have a cis one, 12 hertz, and the geminal one, 7 hertz. HC will see a lot. We're going to see it'll have HA. A and C was trans relationship, so that's 17 hertz. It will have the 12 hertz for the cis relationship to HB, and then it will also have the 2 hertz relationship for HD. So we're going to have a mess up there at 5 to 6 ppm. We're going to have doublets of doublets, doublets of doublets, and then this like doublet of doublets going on. So it'll just be a big old mess. Let's see what HC will look like, though. HA, HB, they're going to be just doublet of doublets. HB will be slightly closer together of a set of doublets than HA will be. But HC, that's an interesting one. So we have first split by 17. Okay, I'm going to totally run out of room there. All right, let's look at HC. First, we split by 17. Then we're going to split by 12. I should draw the lines, shouldn't I? Then we split by 12. and then we split by 2. And so we have a doublet of doublets of doublets. Isn't this so exciting? Let's take a look at what this will look like. This freaking mouse keeps turning off. Good, it wants to save power, but alright, let's see about. Let's look at propylene's NMR. I'm sorry, this was not propylene. What was it? We have, oh, it's some isopropyl thing. No, this is the different molecule. Was it? No, this is the right one. Gosh. Isoaniline, okay. Isoaniline. This is not the right molecule. Phenolphthalein is normally 1, 2, 3, 4, 3 methyl butene NMR. Ah, here we go. So, let's take a look at what we're going to see here. Now, this depends on how good of an NMR you have, how good your splitting is going to be. Notice at 5 to 6, we have this complete mess of stuff happening. So, we're going to have for these 3 are going to be where our mess is around 5 or so. Be theirs. Why is it shown as a quartet? It should be a doublet of doublets. Oh, this is terrible. They're just using n+1, so they're not even using these other ones. Okay, hold up. This is a bad example. Yeah, we see a mess there. Is this going to be the mess we want to see? Not quite. Well, suffice it to say, I don't have this particular example for us, but we end up with a mess there. No. Hard to just look these up, so which is a good thing for me. So, oh well, we tried. Couldn't get this one to quite show up, but that's what we're expecting with all this. We're going to see a mess. Suffice it to say. So we're going to see a doublet of doublets here, doublet of doublets here, and we're going to see a doublet of doublets here. All right, and so we're going to see this. If we had a very nice instrument that's capable of resolving these, otherwise they'll be blobbed up. Oh, that's why I was looking at carbon NMR. Okay, so that's the problem. So there we have it. This is as complex as it gets. Because clearly it's not complex enough, right? But suffice to say, if you have different coupling constants, which occurs when you have some double bonds in there, and you better believe I will be giving you some with double bonds, we're going to see that that's when you get these weird splitting patterns. So I'll be sure to magnify those regions of the spectrum so you can see them on your exam. So you can tell me which one is HA, which one's HB, which one's HC. All that fun stuff. All right, let's see common patterns. Let's see, we have isopropyl is going to be a septet plus a doublet. An ethyl group. These are typically called isolated ones because if they weren't isolated, we would have other things happening with them. An isolated ethyl group will give you a quartet plus a triplet. An isolated methyl group is just a singlet. Interestingly, if you have a para substitute, or for us 1,4, this gives a very symmetrical set of um, peaks in the 7 to 8 region. So typically this axis is reversed 7 to 8 or something. It gives you this very nice symmetrical doublet of doublets. Let's take a look at that so we can see what that looks like. How about we do if we take a look at this NMR, I don't know what this particular thing is. It's in Mandarin, but let's take a look. That is nitroaniline. Okay. Notice what we see at that 7 to 8 region. We see a nice pair of doublets that are symmetrical to each other. So we kind of have the closer ones are a little bit higher than the outside ones. This is a para substituted benzene ring. Sorry, a 1,4 disubstituted. I'll be clear with my language. We haven't learned para yet. But those will show up nicely opposite to each other. Let's see. We'll have some nice. Oh, here we go. Look at this. Look at this. Lovely, lovely symmetrical peaks there. So a para disubstituted. Sorry, 1,4. Let's see. What shall we do? Nope. 1-bromo 4-chlorobenzene. Yeah, let's do that. That should give us a nice set as well. Let's see here. Indeed, we... Oh, this is carbon NMR. Never mind. Don't look at carbon NMR yet. We haven't gotten there. Proton NMR? This is bromine and nitro, but that's the same idea, right? You have two nice symmetrical peaks because they're on opposite sides of each other. We have 4 aromatic hydrogens. Those show up symmetrically in as a doublet of doublets in your molecule. So nice patterns there. So that's what we're looking for. So these are nice patterns for us. The rest are kind of hard to tell. All right, you might have to think about them. But these are patterns. These will give you hints. If you see a doublet and a septet, particularly a doublet and septet worth 1 and 6 hydrogens respectively, that's pretty clear you have an isopropyl group somewhere isolated. Isolated means you might have an ether or a carbonyl or something else that doesn't have CHs next to it. So important stuff there. All right, let's just talk about the integrations right now. Integrations are the easiest part of this. This is all a very complex topic, right? Integrations tell you how many of each H you have. And the integrations are super useful in telling us that. So we're going to see that the integrations are either going to be given to you as some numbers. Let's see. Let's just look at some. This is kind of terrible. Here, let's look at something simple. Let's look at ethylbenzene. Ethylbenzene and NMR. There we go. Let's see if we have integrations on this. All right, we have integrations. Okay, so ethylbenzene, we're expecting a quartet and a triplet, and then this mess of aromatics, which indeed we do see. Let's look at what these integrations are going to be. A little bit, oh god, these are all mixed up, aren't they? Ugh. Okay, let's find one that is not so selective with its peak picking. Where would we have some nice integrations? No, that's no integrations there. Ugh. Integrations, the numbers are nice for us. Is this going to give us integrations? Nope. Well, suffice it to say the integrations. Here, let's just we'll do this our own way. All right. Oh my god, I didn't even switch over to the Google. Okay, well that's good. So so that worked out. So ethylbenzene, we see we're gonna have our triplet here. A quartet here, and then a whole mess of stuff at 7 or so. Roughly speaking, this is my hand-drawn NMR spectrum. You're going to see numbers like this. And this one is going to be... These numbers are the relative areas under the peaks. These are the integrations. These are the areas under the peaks. And they will tell you how many hydrogens you have. Typically, when you're given something like this, you could just be given, so if I'm being nice, I would just tell you how many of each you have. Or I can give you integrations. Integrations like these, what you'll do is you'll just kind of find the common denominator for all of them. Take all your numbers and divide them by your smallest. And you'll get your ratio. I may not tell you exactly how many there are. For example, if you do this 19.9 divided by 19.9, you get 1. 30.6 divided by 19.9, you get 1.5, thereabouts. 51 divided by 19.9, you get 2.5, or thereabouts. And this tells you the ratio of them all. So, just like with empirical formula, you probably want to multiply things to get them to be nice. And so you want integers, so you may need to multiply. Or you can just look at it and say, oh, 2 to 3 to 5 ratio. I mean, you can probably do that 20, 30, 50, 2 to 3 to 5. And so that's, you don't have to do the math, but that's what we'll see here. So what this tells us is this quartet at 2 ppm has 2 hydrogens that make up that quartet. So there are 2 hydrogens that gave this signal. There are 3 hydrogens that gave that signal, and there are 5 hydrogens that gave that mess of a signal due to the anisotropy there. So this tells you, the integrations tell you how many of each hydrogen you have. Hydrogen type. Remember, we have a lot of equivalent hydrogens in this. And so we see that if we had this ethyl benzene, we saw 3 peaks on it, right? Normally benzenes give you a whole mess at 7 to 8. You'll only see nice things with the 1,4 disubstituted ones, unless you have tri-substituted symmetrical ones, but never mind. It's a fun topic, isn't it? It's very complex. We see that these peaks, if we're looking at this molecule, we're expecting this to be about 1.0. We're looking at that to be a triplet, and we're looking at the integration to be about 3 hydrogens, not about 3 hydrogens, 3 hydrogens. That's what we're looking at there. Right? We can predict it. And indeed, lo and behold, on our spectrum, we see here at 1 ppm an integration which gives us 3 hydrogens, and it's a triplet. And so that's what we're looking at there. Here we're looking at about 2 ppm or so, maybe a little higher because next to aromatic is maybe going to be 2.2. We'll predict it. We'll expect this to be a quartet because there are 3 neighboring hydrogens. And we expect this integration to be 2 hydrogens. And then the last one, the aromatics, who knows, we're just looking for 5 hydrogens around 7 ppm. No splitting for the aromatics. Well, I mean, they're split so complexly that we don't even think about it. The anisotropy and all those double bonds, it gets very messy. So aromatics usually we just see as a blob. So fun stuff. Let's take a look at an example because these I've given you I think 25 problems to look at on Canvas. Let me pull them up, and then we'll swap over. One sec. Oh my gosh. All right, I'm on Canvas. I'm going to go to our spec practice. Let's take a look at what we're in for with all this stuff. So, actually, let me just download it. It'll be easier. One sec. And then I'll switch to that screen. Okay. So, with this, we're going to be able to take all this information. You're going to be given an IR spectrum, a proton NMR, and later we're going to see carbon NMR. That one we haven't learned yet. But we're going to be given these 3 spectra, and you're going to give me a structure. That's all this is. Seems so easy, right? No, not so much. In a separate document, you have the formulas, the molecular formulas for these, which you'll need because we haven't gone over mass spec. So this particular problem has C12H18 as its molecular formula. I'm going to write that down for now. We'll come back to it in a second. Where are we here? Let's look at its IR spectrum. Do we see anything of use? Kind of hard to say. Probably not. There's no heteroatoms in this, so we're not really expecting to see much in the NMR or the IR, so boring. Let's look at the NMR. Let's see what we have. We have how I would go about writing this is we have a singlet at about what 7.2 ppm. and its integration is 28. If we look here, we probably have 7 is our lowest number, but we'll see. We'll see 28.1. We'll get there. We have at 3 ppm or 2.9, we have, what is that? 1, 2, 3, 4, 5, 6, 7. We have a septet at 2.9 ppm. That has an integration of 13.8. And then at 1.3, we have a doublet. And that one's worth 83. So I'm just copying down all the information we have for this proton NMR spectrum. And this is how I would do that. So we have a singlet at 7.2 worth 28.1, and so forth and so on. So if we divide all these, we get, what is this? Divide by this by 13.8, that's probably what, 6? 1, probably about 2. If we look here, this is only 9 hydrogens, right? They're all integers, but we only have 9 hydrogens. Our formula has 18 hydrogens, which tells us we actually have twice as many of these, right? So we really have 4 hydrogens here. We have, what's this going to be? 2 hydrogens here, and 12 hydrogens of this type. Do we all see why that is? Because the ratio will give us 2 to 1 to 6, which is the ratio. That's 9 overall, but we have 18 in our molecular formula, which tells us that we have twice as many of those, right? This also tells us that there's probably some symmetry here, because if we only have 3 signals, we only have 3 types of hydrogen, there's probably some symmetry happening with this. Let's see, what else do we have? What information do we have? Well, we have a singlet, which tells us that there's no neighboring protons that are not equivalent for this one. So we have no unequivalent H's nearby. We see a septet and a doublet in a 1 to 6 ratio. That's an isopropyl group. This probably tells us that we have an isopropyl group here. Isopropyl group. Right? 1 to 6 ratio, septet, doublet, pretty good indicator of an isopropyl group. And since we have 2 of all these, we probably have 2 isopropyl groups. And they have to be related by symmetry because they're showing up exactly the same places. So we have 2 isopropyl groups in this molecule, and there's some symmetry there. How do we know there's symmetry? Because they're showing up. We know that 2 hydrogens and 12 hydrogens, one isopropyl group is 1 and 6, right? An isopropyl group is a 1 to 6 ratio. And so if we have 2 and 12, that's still a 1 to 6 ratio. And since they're showing up exactly the same places, that means there's symmetry. So somewhere in our molecule, we have another isopropyl group that's symmetrical to this one. So we have 2 isopropyl groups here, and they are symmetric, whatever they may be, wherever they may be. The last thing we want to think about is where these are going to be showing up. We have 7.2, that's the aromatic region. We have 1.3, that's just a plain old alkyl. And then this 2.9 business. Well, considering what else we have a regular alkyl group. It's a doublet. CH3s showing up about 1.3. That's okay. Plain old alkyl. But we have this other one that's about 2.9, which is a little bit strange. So there's something de-shielding it nearby. And whatever that may be, again, I don't want you to focus on exact numbers. Don't be like, well, I'm going to subtract 1.7 and I get 1.2, and what's 1.2? Don't worry about that. Show up, look at regular regions. That's something that's next to aromatic. Right? Something that's benzylic will show up around 2.5, 3, thereabouts. And so, with all this information, we know we've got an aromatic with 4 hydrogens, and we've got 2 isopropyl groups, which makes sense. So we have a couple ways of doing that. We have a couple options that would give us similar values. And so now we have to consider, okay, well, we had information bits. The aromatic ones, so they had no unequivalent hydrogens. We had a singlet there. A nice singlet. No unequivalent hydrogens. With this one would give us 2 different types of hydrogens, right? The purple ones would see the isopropyls, and the green ones would not as easily. And so these are not identical. If we looked at this one, the blue ones are identical to each other, but the green ones and the purple ones are not. We would have 3 different types of aromatic protons. We were going to see a mess there. We would also see a mess for the left one. But notice the symmetrical ones. This one sees 1 isopropyl group. This one sees 1 isopropyl group, 1 isopropyl group, 1 isopropyl group. These are all equivalent to each other. And we also noted our isopropyls had to be symmetric to each other. So we need them to also be symmetrical, or in the identical environments. And so it's actually better for me to write identical environment here. That would be better. The symmetry part is more this 4 hydrogens here that show up as a singlet. And so we're going to see that the structure for this molecule will be this. And let's go ahead and check the answers and watch. I'm completely wrong. But let's go to Canvas and check our answer. Canvas, here is the key. Lo and behold, diisopropyl benzene, 1,4 relationship. That's what we're looking at. And so, I'm not going to that away. All this is for you. This is going to take time. I understand we have an exam on Monday. That exam does not have any of this information, but still, it's super important for us to know. And so, as a result, tons of practice is necessary. So I've given you 25 sets of spectra. Some of them have heteroatoms, some do not use the formulas. Remember here I have, you'll need the molecular formulas because we haven't covered mass spectroscopy. So you'll need these molecular formulas as you're doing the structure. So I will give you molecular formulas. You have 25 of them. You'll also have 25 sets of spectra. This one is number, here, let's go to a random one. This is number 11. You have an infrared spectrum, You have a proton NMR. This one's nicely spread out for us, so we can see the splitting very nicely. And we got some bizarre long-range coupling, so we might see something a little strange here. And then we have the carbon NMR, which I'm going to do in a different video. Here again, we have some IR data. Oh, look, we have a peak at 1700. I wonder. We have some weird long-range coupling here happening. Peak at 9.5. Peak at 200. We have some interesting things here. That's usually one that doesn't get split, but that's interesting. We'll see. Oh, that's the long-range coupling. Yeah. So whenever you see this note that says spin-spin coupling is observed between non-adjacent carbons, that just means there's extra splitting happening. Now for this one, you see we've got a nice triplet, sextet here, triplet here. Ooh, doublet of doublets, and maybe this might even be a doublet of doublets. Maybe. Do we see here that these are doublets? We might just have two doublets of doublets. We'll see. Who knows? Carbon NMR, we'll see later. Look, another peak at 1700 in IR. Nothing else. Look at all this fun stuff we've got. We got some stuff here in the aromatic region. We've got some stuff down here at aliphatic. We've got some carbon NMR. Blah, blah, blah. This is the idea. So IR kind of useless, right? IR seems... Do we have anything? Aha! Here's something with this. Notice this thing here on the left. That's probably an amine, right? That's probably a primary amine. Two-fingered NH stretched there. Probably has some nitrogens in this molecule. So this is something that takes practice. All right, so you have 25 problems. I also have some just kind of worksheets for you to work on. So just kind of looking at different types of hydrogens, just identifying symmetry. Here's a couple more, or here's a take this molecule and predict it. Do all these predictions. That'll help you too. Here's another set. Here's one with a molecular formula, carbon NMR, IR, proton NMR. Do these things. All right, so there's more practice on this one. All right, there's one more last hint I'm going to give you. And then our last video will be on carbon NMR. This thing, by looking at the molecular formula, it's going to give you hints about what sort of, how many double bonds and stuff you might have. This is the index of hydrogen deficiency. And so we have a formula for this, which is the formula I use. Yeah, this is about right. So IHD is your number of carbons plus number of nitrogens over 2 minus X over 2 minus H over 2 plus what? X are halogens. I'm going to get rid of this number sign here. The IHD of a compound will be equal to number of carbons plus nitrogen over 2 minus halogens over 2 minus hydrogens over 2 plus 1. And this number is valuable because one IHD tells you the number of double bonds and or rings. So a benzene ring, Benzene, just by itself, C6H6, let's plug it into the formula. The IHD of this is 6 plus 0 minus 6 over 2 plus 1, which is 4. Obviously, you don't need to fill in nitrogen and halogens here because there are none of those. A benzene ring has an IHD of 4. We have 3 pi bonds and 1 ring. That's 4. Each pi bond, each double bond, counts as 1 IHD. Each ring counts as 1 IHD. So benzene, which has 3 pi bonds and 1 ring, gives you an IHD of 4. So this will help you as well. Knowing the IHD of your molecule, that tells you how many double bonds you have. And so whether those double bonds are to oxygen, or if it's a triple bond to nitrogen, like a nitrile, or if it's a triple bonded carbon, an alkyne, or if you have rings or whatever, you'll have to use all this information to figure that out. So IHD tells you the number of double bonds or rings. And I would say not even double, I would say pi. Pi bonds. Because you could have a triple bond. Triple bond is 2 IHDs. So like something like this. The formula for this would be C2H3N. We see in this molecule that we have these things, right? IHD would be 2 plus 1 over 2 minus 0 over 2 minus 3 over 2 plus 1. Doing this, you get 2. And indeed, we see 2 pi bonds here. So this would be a good thing for you to do first step, honestly. If you do the first step of these, it tells you how many double bonds or rings you might have in your molecule. And that'll be very important information. Typically, if you have an IHD of 4, you'll probably have a benzene in there. You have an aromatic. How would you verify that? Well, you look at proton NMR. Do you have anything at 7? Probably, then yeah, you've got a benzene. Carbon NMR, do you have anything at 150? Well, you don't know that yet, but those would be other ways to tell. You could also tell your nitrile here. You could tell by IR. You could say, okay, well, I have no end peaks above 3,000. I have this nice peak at 2,300. That's probably a nitrile. And so you'll see that as well. So there's so much information here. Spectroscopy is a very different monster. You have to piece all these pieces of information together. I have a septet here with 2 hydrogens. I've got this here with this many hydrogens. I've got this aromatic thing. I have to figure out how to arrange these groups on my molecule. And so all these, do I have a primary amine, a secondary amine, a tertiary amine, a nitrile? There's all these things nitrogen can do. So there's a ton of work associated with these. So your exam is going to have 3 problems. That's it. Because these take so long. There's so much information that you can get from these spectra. IR, carbon NMR, proton NMR. All very, very important. All very, very useful. Proton NMR most of all. That's why we spent 2 days on it. Carbon NMR is going to be a shorter video. I'll just do that separately and I'll upload it by itself. Because that's going to be a 20, 30-minute video. It's not long for carbon NMR. So, yikes. All right, so we've done it. Get to work. Don't submit these to me. I gave you the answers. I want you to do that, all of these by yourselves. Do them all once, then do them all again. Practice, practice, practice. So that's what I suggest. All right? So Friday, let's do a review, because you do have an exam, although your exam is not on this at all, so you can worry about this later on. Let's do a review Friday at 10 o'clock. I have another review at 9, so we'll do 10 o'clock for you guys. All right? What class is this? 221. Get to practicing. I'm pretty sure the end of the chapter will have some as well. Oh, yes. Oh, yes. Oh, there's plenty of them. Yeah, so I would definitely take a look at the problems in the back. There's about 10 or so. Actually, 1, 2, 3, 4, 5, 6, 7. There's only 7. So aren't you glad I gave you 25 others? So, fun. All right, so enjoy. Start working on these. Later on, I'll let you know when. You'll have a video on carbon NMR. And next week we'll have our exam Monday, and then on Tuesday we're going to start talking about radicals. So this is probably the hardest point in the semester. We have reached it. Spectroscopy in the middle of all these other things. So you survive this, you'll survive the rest. So have fun as much as that's possible. All right? Good luck.